So the next reaction we're going to learn about is actually halogenations. And this is going to be the adding of X, and specifically Cl2 or Br2. So we can either do one equivalent or two equivalents. So you can see there's an alkyne, Br2, and we actually would add the two things just like we did before. The stereochemistry is trans. We do a Markovnikov type addition, and we get mostly the E, the trans product. Don't worry about the Z. This would be the major product, would be the E. As with only one equivalent, with two equivalents, you'd actually, instead of adding two, you'd actually add four. Next up, I'm going to go through the mechanism for this halogenation. All right, halogenation. We're going to add X2, so Cl2 or Br2, depending on the number of equivalents, it'll make a difference. It's regioselective because it adds to the more substituted carbon, so it's a Markovnikov addition. There are no carbocations, you don't need to worry about rearrangements. And the final product ends up being a trans product where the chlorines or the bromines are on opposite sides from each other. All right, let's look at an example, walk through the mechanism here for this. So what's going to happen is we have a terminal alkyne, so an H on the end of carbon 3 here, number their carbons. You have Br2, got CCl4, this is just a polar A product solvent, so it's not going to be involved in the mechanism. We have Br2. We're just going to start with one equivalent first. So the first step is going to be very similar to what we've done before. The pi bond reacts with the bromine bromine bond breaks, and the lone pair from the bromine comes back and reacts. Alright, so what does that give us from the product of these arrows? We formed a carbon-bromine bond to carbon 2, a carbon-bromine bond to carbon 3, and we broke a bromine-bromine bond. So we have a plus charge on this bromine, this 3-membered ring, bromonium ion. We have a Br minus. Now we have need the Br minus to react, so we can either choose carbon 2 or carbon 3. It'll choose the more substituted one because this is a Markovnikov type addition. So this is like an SN2 like. So the bromine had a plus charge, now it's going to get a lone pair from that bond. So it should no longer have a plus charge. You'll notice that we end up with the bromines on opposite sides of the alkene, which we predicted with our stereochemistry. With the stereochemistry of trans, there's no carbocations, drawn all our lone pairs. We've balanced our charge. Renumber the carbons to make sure we did this correct. 3, 2, 1. That's the first addition of bromine. So let's see what happens when we add another bromine, another Br2. Right, so what's going to happen next? You have another equivalent of Br2, so this is something in excess, or if you say two equivalents, you'd keep reacting. Pi bond reacts, we break the bromine-bromine bond, and the lone pair from that first bromine comes back and reacts around. Now we've gone from sp2 hybridized here to an sp3 hybridized state, so now we can actually draw wedges and hatches. And so I think the easiest way to draw the wedges and hatches is to start out like this. We see the bromine initially, an H there, the methyl, and then the other bromine. We can form one of the bromonium ions. Let's pretend it's from the top. Draw that one in. We also have Br minus floating around as well. Now, as long as there's no solvent around, there's no halogenation, well, the Br minus will react. So remember our carbons. 2, 1. Bromine reacts with carbon 2. It's the more substituted carbon. And again, SN2-like, Markovnikov addition, no carbocations. We end up with the bromines. In each step, the bromines that we added are trans to each other. Then we ask ourselves, do we create any stereocenters, any asymmetric centers? Are there any carbons that are bonded to 4 different things that are sp3 hybridized? No, they're not. So we don't have to worry about saying enantiomers or diastereomers or anything like that in this case. Be careful to make sure if there's solvent around, right? Check that solvent. If there is solvent that's different, be careful with that solvent. Check that. Right? If it's polar product solvent, remember those halogenations will happen as well. All right, the second part of this video, we're going to talk about oxidations and reductions of alkynes. So we have one type of oxidation this time. So just one type of oxidation, the oxidative cleavage of alkynes, and we're using our old friend ozone, O3. Before ozone would give us ketones and aldehydes. With a carboxylic acid, with a alkyne, it'll actually give us carboxylic acid. So you split it in the middle, and you actually get, so this is carbon 1, this is carbon 2, carbon 1, and carbon 2. So here's a real example. You cut it in half, you actually get 2 carboxylic acids. So if it said 1 and 2, so instead of making ketones, because it's an extra pi bond, you'll actually have another thing to oxidize, so you get carboxylic acids instead of ketones or aldehydes. So that's the oxidative cleavage of alkynes with O3. Mechanism you don't need to worry about. You learn the mechanism with O3 with alkenes, so no need to worry about the mechanism here. So now let's focus on reductions of alkynes. So this one's going to get a little bit more in depth. There's a couple different ways. There's ends up being 3 ways to reduce alkynes. The first one you already know. That's using H2, palladium, platinum, or nickel. When that does, it does a cis addition, but then it keeps adding. So if you have H2 and an alkyne, it'll go to an alkene and then go right to an alkane. You can't stop it. So this one, you just keep right on reacting, just like you did before. Any pi bonds, H2, palladium, platinum, or nickel, just keeps reacting, and you get 2 cis additions, but you end up with an alkane. Now, if you wanted to stop it at the alkene stage, there's a way. That's the second new way. It's poison catalyst called Lindlar's catalyst. Again, none of these you need to know the mechanism for, but you need to know what products you get. With Lindlar's catalyst, you may take an alkyne and turn it into an alkene. But you'll notice it stops. You still see that cis addition, but it won't keep reacting, unlike the H2 platinum, palladium, or nickel. So Lindlar's will stop at alkenes. It goes from alkynes to alkenes. And it gives a cis addition, so it gives a cis alkene, or a Z. All right, so the third and final way for reducing alkynes is if we want to get a trans alkene. So if we wanted to get a E alkene, how will we do that? We use that dissolving metal reduction. So sodium, or sometimes you'll see lithium dot. These are all sodium dot, lithium dot. They just use metal dissolved in liquid ammonia. And we're not going to worry about the mechanism here yet. We'll learn it later. But what happens here, instead of getting the trans or the cis like we got with the Lindlar's catalyst, we get the trans alkene. So you go from alkyne to alkene, but we get the E or trans alkene instead. So there's 3 ways to do reductions of alkynes. Alkynes all the way to alkanes, and then the 2 ways to get cis and trans. You need to know those, but none of the mechanisms for any of them.